is going to focus more on degrees of freedom in the double copy, or the counting of states. Yeah. So there's a slogan that Zvi likes to have. Well, Zvi's a great guy for slogans, but one is 4 is 2 squared or something like that. So a lot of this lecture is going to focus around expanding on this slogan and various versions of it. So you just hopefully see the relevance. Okay, so now you might see people saying that the most basic double copy is something like this, for 3-point trees. You take a 3-point tree in Yang-Mills, you square it, that's a 3-point tree in gravity. Now, there is actually a more basic statement of the double copy, and that's kind of really what I want to talk about today, or today in this lecture. But really the most basic double copy is for states. So what I mean is that there's a state in Yang-Mills theory. It says there's 2 plus and minus helicity gauge bosons, 2 per momentum p. And those states themselves double copy into states in gravity. Right? And it's kind of interesting to see how that works out. I think it gives you, you actually begin to understand the inner workings of the double copy, which otherwise can appear like, just seem like a total miracle. It's just magic. Okay. Now, to see how this works, what I'm going to do is spend, I don't know, half the lecture just talking about waves, plain, wave solutions in electromagnetism and in gravity. Right? Now, the double copy always relates Yang-Mills theory to gravity. But when I'm just going to talk about states, there's no interactions. So there's no difference between electromagnetism and gravity. Right? So if you're in a situation, and we'll see a lot of the situations like this where the interactions are somehow not so important, then the double copy simplifies and becomes about E&M, electromagnetism and gravity. So let me begin with a reminder. This will be a basic reminder. Reminder of plane waves in E and M. In E and M. E and M's electromagnetism. Okay, well, the story is very simple. We're solving the Maxwell equations. We pick a gauge. So the gauge is Lorentz gauge. Lorentz gauge, d mu, a mu equals 0. The Maxwell equations are d squared a mu equals 0 in Lorentz gauge. The solutions are a mu equals a linear combination of things like epsilon mu e to the minus I k dot x. Right. So now, the Maxwell equation is solved provided k squared equals 0, obviously. So we need 2 things. We need k squared equals 0 and k dot epsilon equals 0 as well, because that's what the implication of the Lorentz gauge condition is. Okay, so very good. So we have these solutions, but there is still some residual gauge invariance left, right? And that's an important thing here. So gauge transformations act on these solutions. Well, gauge transformation is just a replacement of A with A prime, which is A plus d mu lambda, right? In terms of the polarization vectors, that's this replacement, which I also talked about this morning, epsilon prime. So you replace epsilon with epsilon prime, which is epsilon plus k mu alpha. Now, this epsilon prime automatically satisfies the Lorentz gauge condition because since, well, k dot epsilon plus k squared alpha equals 0, right? Separately, each of these two terms separately 0. So, so we still have freedom to make a gauge transformation. I still have this parameter alpha running around, and I can use it for some reason, right? And often what we do in amplitudes is we pick another gauge. So we pick, so we pick another quantity. We pick a vector q, such that q squared, q dot k is non-zero. So, and then I can impose, q dot epsilon prime equals 0. Right? There's always a solution, because if you give me, or maybe Radu here, Radu isn't here, Radu gave me a really nasty gauge vector. It's just that kind of guy. He's not here, right? Yes. Well, so then I can add, so epsilon prime is epsilon plus k alpha. So when I dot it with q, I got q dot epsilon plus q dot k alpha. So I'll often should set q dot k equal to 1. Let me see. So I can just set q dot k equals 1 by scaling then, right? So if this is 1, there's obviously a solution for alpha, setting this polarization, this dot product to 0, and the solution is just alpha is minus q dot epsilon. Right? Okay, so what I've done now is we have a polarization, this epsilon prime. It satisfies k dot epsilon prime equals 0 and q dot epsilon prime equals 0. So that's two equations on the four, components of the polarization vector, which is another way of saying that there's only 2 degrees of freedom in, the perturbative waves in E and M. Okay, so there's 2 states. And note that we have a basis. Which is, the 2 epsilons, now let me call them epsilon plus and minus, k mu, q mu. Sort of handy, and I'll use that in a moment. This is a basis of the 4-dimensional space of vectors. Okay, so that's E and M, very straightforward. Hopefully that's reasonably clear, although if there are questions, of course, it's a good time to ask one. Things are hopefully reasonably spectacularly not too complicated. Good. Okay, so what about in gravity? So in GR, so I'm going to linearize, so I'm just looking at linearized waves for now. Well, the Einstein equations take the form. So the Einstein equations are, so we can write them as d squared h bar mu nu equals 0, where h bar is the metric perturbation trace reversed by adding this term here, eta mu nu h. And I'm in the gauge, sometimes called the Donder gauge, d mu h bar mu nu, oops. Right. So this is just writing out the Einstein equations in this gauge. Okay, so, well then the solutions are very similar to before. So h bar mu nu, I'm going to call it a polarization tensor, e mu nu, e to the minus I k dot x. So this polarization tensor is symmetric, right? Because this h bar is basically just defined in terms of the metric perturbation. The metric perturbation is symmetric. So e mu nu is e nu mu. And because of this de Donder gauge condition, we have to impose k mu e mu nu equals 0. Okay, now again, as in the case of E and M, this doesn't uniquely fix the polarization tensors by any means. There's some residual gauge symmetry, and we can use that to simplify our understanding of these polarization tensors. So, well, what is the gauge symmetry that we have left? Well, the gauge transformation of the perturbative metric is, well, the gauge transformation of H is an easy one to remember. you just get to add a symmetrized derivative of a vector field to the metric. Okay, but the e's come from h bar, so we need to figure out what that means for h bar prime. So, well, some of it is similar, plus d nu c mu. But now there's this minus a half eta mu nu h. So I have to take the trace of this. They come with a factor of 2. Got to kill that 2. This is all in 4D, by the way. So we're going to get an additional term like this. Okay, so it looks a little bit complicated to begin with. But actually, all these terms are good. So what they mean is, in terms of the polarization tensor, you can gauge transform the polarization tensor into this form. So write it as k mu. I'll say the Fourier transform of this xi is an alpha, or something which is easier to write, plus k nu alpha mu minus eta mu nu k dot alpha. Okay, good. So that's sort of what I need. Now, the first thing to note about this is if E mu nu satisfies this, this de Dondert condition, well, so does the E prime. So to see that, we can compute what k mu dotted with E prime is. It's k mu with E mu nu. So that satisfies de Dondert, because that's what I started with. There's a plus k squared. K squared is 0, right? Because that was the Einstein equation, basically. Then there's a term plus k nu k dot alpha. And now this additional term helps me by giving me a k nu k dot alpha with a minus sign. So indeed, you're always in de Dondert gauge. Okay, so that's good. I have an alpha mu now, a 4-vector thing to play with, which I can use to simplify my polarization tensors. All right, so so we have residual gauge symmetry. So I am going to use that symmetry to impose 2 constraints on my E. So so there's 2 constraints that you can go ahead and impose. They're consistent. The first one is I'm going to require my E to be traceless. And the second, I'll require my, I'll pick the same gauge Q, the same, yeah, so somehow I always call this a gauge vector. This Q, I'll pick a Q and I will demand Q mu, E mu nu equals 0. Now you can go ahead and check that these are both that these are possible. So for example, one is possible. So E prime mu mu will be so I want it to be 0. It will be equal to the trace of whatever the original E was, plus these things here. Plus, well, there's going to be 2 k dot alpha from these 2 terms, minus 4 k dot alpha from here, so minus 2 k dot alpha. So in other words, there's a solution for k dot alpha in terms of the trace of the original metric perturbation, the original, polarization tensor. So that uses up one of my components of alpha, right? It leaves 3 left. The 3 left you can use to impose equation, this condition 2, right? You might think, oh, look, there's 4 conditions here, but there's really only 3 because you automatically satisfied the de Dondert gauge condition. So there's really only 3 conditions left. And you can go ahead, that's an exercise. I like setting exercises. So check 2 is possible. Now, in order to do that, it is convenient to use this basis. Right? This sort of basis is a bit designed for that purpose. You're trying to check that if I dot it with the Q, I'm going to get 0. Well, that leaves one dangling index, the new. I could contract that dangling index with these 4 vectors. If I dot it with that guy, it'll be trivial. So there's 3 equations to work out, and you can just see that this involves fixing the 3 components of alpha on that basis. Right? So there's always a solution. Anyway, that's worth going through the details. I'll do a sort of similar thing here in a moment. Okay, so good. Any questions about that? Yeah.
So you are saying that we are coming to that there are 2 degrees of freedom.
Yeah, this is just an explicit way of computing it. Yeah, and I'll get it even more explicit in a moment.
So
Yeah.
it works on higher dimensions.
Yes, it does. I'm just doing 4 dimensions here, so I don't have D's, capital D's, number of dimensions running around the place. But yep, you can do this in higher dimensions, no problem.
There's a way that we see that in higher dimensions, or like for 4 dimensions, it's easier when you can take a space, the space slice,
Mm-hmm.
then you integrate your direction of k
Uh-huh.
to be perpendicular to that slice, and you see that the radiation degrees of freedom like there.
Ah, yes, you can do things like that. Yes. Yeah. Well, yeah. Maybe we're getting there.
In higher dimensions, you don't see that.
Oh, okay. So, well, let me see. Maybe the summary of the question is there a difference between doing this in higher dimensions and in 4 dimensions? Would that be fair? That's kind of what you're asking about? I mean, you used a specific idea, but I mean, like in terms of this argument, the higher dimension version is exactly the same. There's d minus 2 vectors here. So there's t minus 2 polarizations in Yang-Mills, or E and M. There's some d's running around here, so that these steps work out. And the stuff over here all works in a very similar way. People think about this in different ways. This is just this is a scattering amplitudes point of view on the degree of freedom counting. Yep. Well, so what I'm saying here, for example, is this fixes one of the components of alpha. It's the component of alpha that's projected out by k, right? So it's the k dot alpha component. And yeah, so there's in 4 dimensions, I've got 4 components in alpha. Yeah. And exactly, you need to use the 3 other components. You'll have a q dot alpha component, and then an epsilon plus or minus dot alpha component to satisfy this condition. Okay, yeah. Any other questions? Okay, very good. So, these are conditions that we can impose, but to make the meaning or the importance of these conditions as clear as possible, it is very convenient to write out what the polarization tensor is in terms of this basis, right? So here's a basis. It's a basis of vectors. Okay, I got them by solving the Maxwell equations, but that doesn't matter, right? It's just a basis of vectors. So here's a basis of vectors. I can choose that basis of vectors as a basis of the tensor product space that my polarization tensor is sitting in, right? So we can always express, independent of gauge conditions, always right, that's correct. So I could always write that my polarization tensor, this is, say, the primed one, the one I want to impose gauge conditions on, I can always choose to write it in terms of my basis there. So now, I'll have a sum here. Right. So I here is the 2 components of my polarization vector. Right. So this is resolving this polarization tensor onto this basis. There's more terms, right? There's going to be a term where I have one polarization vector and one k. So these symbol here, this brackets just denote symmetrization on the indices mu and nu. Plus ci epsilon I mu Q nu plus A, B, C, D. I can have K mu plus E K mu Q nu plus F Q mu Q nu. Right? So this is just so I'm using this basis of the tensor product space, right? So now I'm imposing symmetry in the mu and nu indices. So there should be 10 components, you know, I mean, these A's, B's, C's, and D's, etc. There should be 10 of them, and hopefully there is. Yeah, there's probably 3 there. 5, 7, 8, 9, 10. Right. So this is just the expression of a general symmetric 4x4 tensor on a basis. And I just picked this particular basis, right? But now I can go and impose these conditions. There's these 2 conditions and the de Donders condition, right? So I can impose these to fix some of these numbers here, these A's, B's, C's, and D's. So, so the de Donders condition. Okay, so if I dot in here with the K mu, well, it'll first of all hit these vectors epsilon here. Well, those were designed so that epsilon to K was 0, so I don't have to worry about those. Then it will dot in here. It'll hit an epsilon or a K, right? Again, those were designed so that the dot products were all 0. So the next thing that could happen is my K can come in here. Now here it could hit an epsilon. Again, that's not going to give anything interesting. Or it could hit against a Q. And I chose K dot Q equal to be 1. Right? So that is not 0. So I will get a term out of that. It'll be Ci, C lower I guess, epsilon I mu times 1 when the K contracts into the right thing. This one won't give me anything. I'll just get K squared equals 0. Here I can get something, plus E K mu. And I can also get something from the F Q mu. Right. So all of the, so this equation must hold. But remember that epsilon, K, and Q are a basis. Right? So there's no relations amongst these. It must be that Ci, E, and F are all 0. Right? So you just get to drop these. C, E, and F are 0. Similarly, Q mu, E prime mu nu, equals 0. Well, that's just going to tell you that the B is 0. Bi equals 0. Or the D. Yep. D is 0. Good. Yeah, so this guy's gone. And this guy's gone. Right? And there's one other condition. E prime mu equals 0. Okay, so the only thing that's got a trace in here is epsilon plus dot epsilon minus. Right? Everything else, epsilon plus squares to 0, epsilon minus square to 0. So the only thing that you get is the component A12. So E prime mu nu is given by just 2 possibilities. Epsilon plus mu, epsilon plus nu, plus A minus minus, epsilon minus mu, epsilon minus nu. In other words, the most general possible wave is a linear combination of 2, right? The waves of definite helicity. So the gravitons of definite helicity, or say, this is a gravitational wave polarization. The polarizations are, so the basis, that's the way to say it, basis of polarizations is E plus plus mu nu, which is epsilon plus mu, epsilon plus nu, and E minus minus mu nu, epsilon minus mu, epsilon minus nu. Okay, so the states that you can get out of the gravity are literally double copies of the states in Yang-Mills. Okay, so with that in mind, I'm going to give you another exercise. Okay, so yeah, this is, I think, straightforward but illuminating. So consider two theories. So one is going to be, Yang-Mills theory. Let me see, maybe I should put a trace. No, maybe I won't put a trace. Minus a quarter. And let's suppose that we have a scalar field theory coupled to this. See, make sure this is what I really plan to do. Yeah. Oh, I see. Yeah. So a scalar in a representation R minus m squared phi dagger phi. Say, so whatever arbitrary representation of the gauge group, and S2 will be so gravity plus a half d mu phi. I guess there's a g mu nu. Okay, so just a second. So this is a theory with a scalar which is minimally coupled to Yang-Mills theory, and here's a scalar minimally coupled to gravity. So what I want you to do is show that that the 3-point amplitude from theory 1, which is something that looks like this at the level of Feynman diagrams. There's an I there, I guess. Let's say that show this is a number times epsilon dot p. Here's p, and there's an epsilon. Whereas the amplitude in theory 2, or the 3-point amplitude in theory 2, this one, with this massive scalar coupled to gravity, is a number times epsilon dot p squared, right? And in order to do that, you'll need to use the fact that the polarization tensors can be written as polarization vectors squared, right? So there's just a straightforward double copy here. The massive 3-point amplitude. You can just get it from the Feynman diagrams. It's easy. Let's see. So who had their hands up first? I think you had your hand up first. Yeah. Yes. Yeah. So let me see. So the question was, let me see. Am I understanding you right? Yeah, that's right. So I've used here that epsilon plus squared equals 0 and epsilon minus squared equals 0. And maybe I used epsilon plus dot epsilon minus, well, plus or minus 1, something like that. Yeah, I'd probably make it minus 1. Yeah, so I mean, you should think about these polarization vectors as being something like, 0, 0, 1, I, 1 plus or minus I. Good. Other questions? Yes. Uh-huh. Okay, yeah, so interesting question. So I guess the question is, since we can build some of these solutions from polarization vectors or quantities in Yang-Mills, can we make that explicit at the level of the entire formalism of general relativity? Well, I don't know. Yeah, that's a tough question. People, including Zvi, for example, Zvi has some papers on writing the Lagrangian for GR in terms of some double copy friendly method. But what tends to happen is the Lagrangian gets extremely complicated. There are many auxiliary fields which you have to integrate out. And there seems to be, sort of order by order perturbation theory seems to be possible, but I mean, it was just very complicated, so it wasn't clear that this was, a fantastic thing to do. But maybe, maybe we don't need to think about everything from the action. So in terms of computing observables from Yang-Mills, well then, yes, I think you can. Certainly any observable in flat space, I believe you can compute this way. And I'll discuss that a little bit more starting from my next lecture, whenever that is. Yeah. Okay. Yeah. Yeah. In many ways, that's one of the things I spent a lot of my time trying to. I spent most of my research time recently trying to answer your question. Okay. Any other questions? Okay. Good. Oh, question. Yes. Yep. Yep. Ooh, good point. Oh, I see. So you want to give this scalar a charge? Yeah. Let me see. Yeah, that's an interesting thing to talk about. So now, if I were to give this scalar field a charge, so let's say I mean, in a way, you're asking me to think of it S3, which has gravity. It's also got a Yang-Mills force, and it's got a scalar, which is minimally coupled to both the Yang-Mills and gravity. That's what you're sort of asking me about, right? And what's going to happen then? Well, this particular amplitude is going to be unchanged. That's the amplitude of just the graviton exploring, the scalar particle. But now in my S3, there will be another amplitude. There'll be, this amplitude and an amplitude that looks a lot like that, right? So then you might wonder, well, how do you get all of those from the double copy? And there is a story about that. The story involves mixed double copies. So if you want, I could start with, another theory. Now, how am I going to do this? So I want, sorry. So this amplitude here double copies into this one. Now, I want something in a sense that, in the theory, the S3, which is the gravity, and it also has this, so you want to get that by the double copy. Well, you can get this from this amplitude, double copied, multiplied by an amplitude with a scalar particle interacting with a scalar particle. So there's a double copy story for that as well. Yeah, actually, that brings me to a topic which I didn't really, I haven't managed to shoehorn into these lectures, but there is a sort of very interesting line of research asking the question, what theories can't be double copied? In theory, under what circumstance can I not get that theory from a double copy? Even just asking for theories which have double copies which have gravity, there's a huge slew of theories that could be made from the double copy. There are some oddballs that people haven't been able to figure out a double copy story for, but certainly there's a large range of theories that can be double copied. Yeah, so I don't know. I mean, it's a question: can you double copy any gravitational theory? I don't know the answer to that. I don't think anybody does. Excellent. Any more questions? Okay, very good. So I'm going to spend most of the rest of the lecture going through a worked example at 4 points with massive particles. But before I do that, I want to just take advantage of this line of reasoning to point something out, which will become more important in later lectures. So essentially what I was arguing so far is that the states in gravity can be understood as double copies of the states in Yang-Mills theory. But it is also true that the actual wave solutions themselves look like double copies. So So the wave solutions, yeah, say of definite helicity, are things like A mu is epsilon mu e to the minus I k dot x. H mu nu is epsilon mu e to the minus I k dot x. So H mu nu is A nu, except you got to divide by an e to the minus I k dot x. So up to some factor, which is like a scalar factor, the wave solutions are themselves double copies. And this scalar factor, which maybe at first looks like a bug, people don't really say that, but actually this scalar factor really is always there. So the slogan, people often say the slogan is, G or is Yang-Mills squared, but that's not really right. The slogan really should be that G or is Yang-Mills squared, but you've got to divide out by a scalar. Now, maybe I'll say more about that in other cases, but it is true, for example, that you can understand the KLT relations as being Yang-Mills, something in the middle, which is an inverse of something to do with the scalar. You could think of BCJ as being, a story about I've got an amplitude. There's some numerator, Ni, Ci over Di. I take that Ci and I replace it with an Ni, but you could also replace, in Yang-Mills theory, you could take the Ni and replace it with a Ci. That will give you a theory with the scalar. It'll have Ci tilde over Di. This is the theory of a biadjoint scalar, which actually plays quite an important role in some of the theoretical developments in BCJ story along these lines. Anyway, so now this also maybe suggests the question, to what extent can we understand solutions of general relativity, say exact solutions, as arising from a double copy? And that'll be a topic of my last lecture. Okay, good. Now, well, I want to do this example now. I didn't say much there, but if there are questions on that, it'd be good to discuss them. Oh, okay. Okay, so this example I want to talk about, just to explore what's going on with the states in the double copy, is a 4-point tree, massive tree amplitude. So what I mean here is I'll have an amplitude, two particles coming in, two particles going out. Right. These two particles will have mass and various charges. So this can be in representation 1 and this in representation 2. They have different masses, just totally different particles, right? Okay, so I'm going to compute this amplitude, and then I'm going to double copy it into gravity, and then I want to talk about what's actually gone on in the in all the steps of that double copy. So there's something to learn about the states. So first thing, let's get our Feynman rules right. P1 prime. Okay, so I happen to know this Feynman rule, and it is this. So by the way, I'm thinking of the charge flow is going out the board. So this is past, and that's the future. Okay, so this amplitude then. So here I'm actually going to, maybe unusually, put all the factors in. So I'm going to use the resulting double copy later on, and I want to get an answer, which makes at least some sense. So here's P1 prime. I'm going to shoot momentum Q between them, P2 prime. Radu, in his earlier lecture, talked about a Q. This Q is going to be pretty much the same Q. This is something that could be involved in a potential. Okay, so let's do the computation. So there's two factors of IG. I'll get TA. This is really TA of representation 1. There'll be a TA for representation 2 hooked together by the intermediate gluon. What else am I going to get? I'm going to get P1 plus P1 prime with some index mu times. There's a gauge boson propagator, which has a minus I, eta mu nu, over Q squared. That's in Feynman gauge. And then P2 plus P2 prime, index nu. Okay, so that's the amplitude. Great. All right, so let's cancel an I and work out what the A is. By the way, so I should maybe say, so this is in the convention where S is 1 plus IT. So that's that I. Not everybody uses that convention. There's 3 I's here. So with that minus sign, this whole thing just has an overall I, no sign, right? So if I divide that I out, then signs go away. There's a G squared, TA1, TA2. From these guys, well, I'm just going to keep these running along for a ride for a while. P1 prime, mu, eta mu nu, P2 plus P2 prime. I'll simplify that, but later. Okay. Now, there is a convention in the world of amplitude. So I've written this out in very standard, like Peskin-Schroeder conventions. So in amplitudes, we tend to rescale these T's, maybe somebody already mentioned that, so that their trace is 1 rather than a half. Right? So that involves fixing up some factors of 2, TA tilde. TA is TA tilde. So these are the more amplitudes-friendly ones over root 2. Let me just leave out that 1, looks a bit funny. So that means that this 4-point amplitude is really G squared over, well, say TA tilde 1, TA tilde 2, and then this thing here. I'm leaving it like this deliberately. There's a factor, there's a half there, and a Q squared downstairs. Okay, so I want to think about this as, so the coupling, which we have to patch up when we're doing double copy anyway, a color factor, this TA1, well, these matrices, a numerator over a denominator, right? So where, the color factor is the TA tilde 1, TA tilde 2. The numerator is, it's got a half, P1 plus P1 prime, mu, eta mu nu, P1 plus P, that's 2, plus P2 prime, nu. Okay, I think that's it, Yeah, and the denominator is obviously Q squared. Okay, so I'd like to double copy this. Now, when we're doing the double copy, well, maybe we need to worry about color kinematics duality, right? It should be, there's this color factor here. Maybe I need to worry about gauge invariance, right? I had this discussion about it this morning. We need to worry about gauge invariance. Here, there is nothing to worry about. There is no outgoing gauge boson, for one thing. So I don't have an outgoing polarization vector that I'm going to fiddle around with. Right? So there is no, there's nothing going on here. Similarly, this color factor here, it doesn't really satisfy. I mean, it's just a bunch of T's. It doesn't satisfy any Jacobi relations whatsoever. But there's no obstacle here. There's no reason why I wouldn't just say, I'll just define a double copy, M, which is kappa over 2 squared. I'm replacing G with kappa over 2. n squared over d. Right? I mean, you might be, it's true to say, I think, that theories, double copies like this, where I've taken a massive particle transforming in some representation and I've just squared it, those aren't as well studied as pure Yang-Mills, according to pure gravity. So here I'm being, say, I reckon this is going to work. Why wouldn't it work, right? I don't see any reason why it wouldn't work, so I go ahead and do it. And it does work. This is perfectly fine. It's correct. I mean, if you're doing this yourself, you might ask yourself the question, what could go wrong, and make sure it doesn't, right? And you'll see in a little bit more detail what I mean by that in a moment, maybe. Anyway, so this is the double copied amplitude. It is literally kappa squared over 4. There's another quarter because this thing got squared. That's one of the reasons why this rescaling is done. It gets the factors right, and we're doing double copy. And then we have this quantity, now it's going to appear squared. P2 plus P2 prime nu squared over Q squared. Okay, 4.3 in a theory of gravity. Okay, yeah, so this thing essentially is something like this. All right, but what, now, there is another way we could have constructed this amplitude. Zvi last week spoke about generalized unitarity. So one thing you could do is say, well, for example, this tree in Yang-Mills theory, I could make it out of 2 3-point trees with a photon or gluon in the middle and sum over those states of those gluons, right? That would give me this amplitude here. In gravity, I could do something similar. In gravity, I could say, well, I know that this 4-point is made out of 2 3-point trees, right? I could build those 3-point, I could compute those 3-point trees. Sorry, Irish people tend to pronounce 3 and tree is completely the same. I'm sorry, this is a problem when you're somebody doing scattering amplitudes, and you're Irish. Anyways, you could build this by generalized unitarity. So it behooves us, it's a good idea to look at what's going on in the factorization channel here, right? So I've built an amplitude. It's supposed to look like this. It's interesting to look at what happens when I multiply by q squared and take the limit where q squared goes on shell, right? Because then this amplitude will break up into a sum of a product of 2 3-point trees. Okay. So let's investigate. So that's one of the things that could go wrong, right? If your factorization channels are messed up, you've messed up. Of this amplitude. So I want to look at this factorization. So in other words, that means I take the amplitude in gravity, I multiply by q squared, and then I take the limit that q squared goes to 0. That's what looking at the factorization means. So lim q squared goes to 0, q squared amplitude. Well, that just cancels off this q squared here. That's right, this is kappa squared over 16. And now I want to write this thing out as p1 plus p1 prime mu, p1 plus p1 prime, another mu, I'll call it mu prime, eta mu nu, eta mu prime nu prime, p2 plus p2 prime nu, p2 plus p2 prime nu prime. Okay, so that's the numerator of this diagram on the factorization channel. This is the kind of thing that you would expect to be getting from generalized unitarity by taking those 2 3-point amplitudes and multiplying them together and summing over the states passing through the middle, right? So through this cut. Now, the thing to notice is this thing here, right? The polarization, so if I really had, and this is the issue here, that I want to know what are the degrees of freedom propagating in this channel. So I'm expecting to get a graviton, right, propagating in that channel. To polarize into Donner gauge, so the graviton propagator, so looking like this, so mu prime to nu prime is, well, there'd be a 1 over q squared, but then there's the numerator, eta mu nu, eta mu prime. There's a second term, eta mu nu prime, eta mu prime nu. And then, crucially, there's a subtraction term, eta mu prime, eta nu prime. So that's what if I had a graviton, only a graviton propagating in this diagram, I would have picked up this numerator, this projector, this index structure, between the p's and the p primes on the left and the p's and the p primes on the right. Now, I haven't picked up that projector. These terms here are more or less the same, right? I mean, there's a symmetry between mu and mu prime, so if I use the symmetry here, these two terms will be the same. But this term, which is present in gravity, is not present in the double copies I just performed it in front of you, right? So now, there's a reason for this, right? What has gone on here is I made, maybe I should write something. So thus we see that M does not only involve propagating gravitons. So there's propagating other particles. So we propagated some other stuff in there that maybe we didn't really want to, right? Now, so there is a good reason for that. Where's my duster? Okay, to see why this has happened, let's think about this construction from a generalized unitarity point of view. So now this 4-point amplitude would be a sum over helicities of these two tree amplitudes. So you would sum over, so in other words, there's two terms with a plus and a minus, and then there's a term with a minus and a plus, right? So that's what you would do in generalized unitarity to build a 4-point. To build a 4-point in GR, let me put a GR, you do something very similar. You would take this 3-point amplitude, and you'd sum over the physical helicities of a graviton. So you'd have the plus graviton going to the minus one, and you'd have the minus one going to the plus. Right? So you'd have this sum. What I did in this double copy is I squared this term, right? Instead, M is, let's write it like this. Yeah, actually, let me write it like this. So this thing has a minus, plus going to minus, plus minus going to plus, squared, right? So one of these terms will, if I square this term, I'll get that term, right? I'll get, maybe it's good to write plus plus. Right, so squaring the first term here, I'll exactly get the first term there. Squaring the last term here, I'll exactly get the last term there. But there are cross terms, right? There's a cross term where I multiplied this thing by this, right? That has a plus minus helicity in it. Plus minus is no helicity, right? There's a plus minus here, that one there, plus minus, times minus plus. No, it's no helicity to no helicity, scalar amplitude. And there's two of them. There are two scalar amplitudes, there are two scalar terms that are being included in that amplitude over there. Right? So that's why I got this projector. Right? So, and that's one of these issues of the double copy. If you really want to propagate gravitons, then you have to make sure, or you have to do something. You know, I mean, you can implement the double copy in various ways. You could implement it here using generalized unitarity and perform the helicity sum after squaring, essentially. Right? If you perform the helicity sum first and then you square, well, you'll get a theory of, you get an amplitude in a theory involving gravity, but that theory will also have scalars propagating. Maybe it's plus, maybe it's minus. It depends on what you actually care about. Now, in our application, we're mainly going to care about amplitudes in Einstein gravity, right? Well, so you might say, well, gosh, this method wasn't very useful, but actually it's not a problem at all. All I need to do is say, look, that projector there, I should just replace it with this projector. It's not so hard, right? And then we will actually, in a straightforward way, deduce the amplitude in gravity. Maybe I should say these extra scalar modes have names. People call them the dilaton and the axion. The dilaton is a real scalar, and the axion is a pseudo-scalar. In higher dimensions, the axion is just an antisymmetric tensor, and the dilaton is just a trace of the metric. Okay, so we can... So... you can simply fix our problem by replacing, well, I guess I need to get the factor of 2 right. Yeah. So what do I have over there? Eta mu nu, eta mu prime, nu prime. So I'll just replace it with the de Donders gauge propagator. Eta mu nu prime, eta... what should I write over there? Mu prime mu minus eta mu mu prime, eta nu nu prime. So the amplitude then in gravity will be what I had here, except I need to replace these, fix up that replacement. So I guess I'll get kappa squared over 32 q squared. Okay. Yeah, so just a little bit of notation to simplify my life here. So there's a P1. We had a Q running across here. So the outgoing one is P1 plus Q. There's a P2 and an outgoing one, which is a P2 minus a Q. Maybe I'll do that. Yeah. Well, do that in a second. Mu, P1 plus P1 prime, mu prime. We have to write the right propagator or projector now. Mu prime plus eta mu nu prime, eta mu prime nu minus eta mu mu prime, eta nu nu prime, P2 plus P2 prime, nu, P2 plus P2 prime, nu prime. Okay. Now, there are situations where, as Radu was discussing a little while ago, where this Q that's going to appear in this numerator, so I rewrite the P primes as P1 plus Q and the P2 as P2 minus Q. All of these quantities here are going to involve a P and a Q, right? Now, Radu was saying that when we're thinking about the classical limit, we're frequently interested in cases where Q is very small compared to the P, right? So when Q is negligible compared to P, we have equals kappa squared over, well, there's 32 Q squared downstairs. But so this will be 2P plus Q. I'm going to neglect the Q. So I'll get a 2 from there, a 2 from there, a 2 from here, and a 2 from there. So there'll be 16. So then this will be just P1 mu prime. This dot product still. Mu prime plus eta mu prime, eta mu prime nu, minus eta mu prime, eta nu prime, P2 nu prime. And now we can just do the dot products. Kappa squared over 2Q squared. Okay, so this, in these two terms, I mean, they're going to be the same. I'm just going to get a P from one side dotted with a P2 from the other side. Right. So these two terms are going to give me a factor 2, P1 dot P2 quantity squared. And this last one, I'm going to just pick up a minus M1 squared, M2 squared. Okay. So, yeah, okay. So, and I'm going to use that in a later lecture just to compute some interesting stuff related to gravitational processes. Okay, that was more or less where I was planning to get to. Am I more or less on time? Or? Yep, excellent. So then I guess it's time for questions. Yep. So the reason to do this, right, is to put the intermediate particle on shell. So there's an intermediate particle here, it's the graviton. It's only when this particle is on shell that this thing will decompose into a product of two 3-point amplitudes. Right? As you know, for an amplitude, you have to have all of the particles on shell. So anytime you put this intermediate particle or some intermediate particle on shell, you should expect your things are going to simplify because they become products of amplitudes. Now, the reason I wanted to do that is, you know, amplitudes have this, well, this generalized unitarity trick makes amplitudes into little things, little bricks of Lego, right? So you can build up this 4-point amplitude from the 3-point amplitudes. But in particular, you know, it just gives you, you know, when the thing breaks up into two 3-point amplitudes, you can really study what it is that's propagating in between. You know, I mean, yeah, maybe it's worth saying that, you know, this, well, if I didn't have this, you know, well, let's write it like this. This is 1 over Q squared, the sum over the physical helicities, E mu prime, E nu prime. Right? So these are the polarization tensors now of on-shell gravitons in the intermediate state. So that's where this de Donders thing is coming from, this de Donders projector. I should say, well, there's plus gauge terms. There we go. So there will be some funny gauge terms in the middle, but they'll cancel away when they're connected into amplitudes. Does that answer your question? Yeah. Good. Yep.
Maybe wait for the microphone.
Yeah, I understand that there is no S channel on the Young-Mills side, but there in gravity we should have an S channel, right? Or shouldn't we? I can imagine.
Let's see. So you're wondering about the Feynman diagram.
Yeah.
Are you saying that why isn't there this?
Yeah. Yes.
Well, I guess because you know, so I'm thinking about these particles as having different masses. You know, so these are quanta of entirely different quantum field theories. You know, phi 1 and phi 2. So so you couldn't have an annihilation of phi 1 into phi 2 unless you know, there was a symmetry between phi 1 and phi 2.
So we just keep in mind the the black holes basically, right?
Yeah, that's right. You're right. I mean, yeah, indeed. Yeah, it's sort of stuck in my mind, so I'm so used to it. But yeah, so these particles are supposed to be totally distinguishable, different masses, different quantum numbers, everything about them being different. Entirely for the reason that I don't particularly want that diagram. Yeah. I mean, if you did have diagrams like this, it isn't necessarily going to, I mean, well, it would be a different theory. So now, maybe it's a theory where I just have one scalar field interacting gravitationally. Then the Yang-Mills theory would also be different. It would also have an S-channel diagram. So the story would be different, but there would still be a story.
Any other question? If not, let's thank Donal again. And we should be back in about 30 minutes.